Welcome to Securing the System, a deep dive into reversing Android pre-install applications with Matthew Stone. Just a couple announcements before we begin. Please stop by the business hall located on this floor, Mandalay Bay. You can also stop by the Black Hat Arsenal today. It's in the business hall as well on this level. We ask you to please put your phone in silence, and please welcome our speaker today again, Matthew Stone. Thank you.
So this is Securing the System. I hope that's what you're here for. My name is Maddie Stone. My pronouns are she and her. And I am, as of 2 weeks ago, a security researcher on Project Zero. But before that, I was a reverse engineer and led our efforts in reverse engineering and finding malware in the pre-installed and the off Google Play ecosystems. So all of the work in this presentation is coming from my work on the Google Android security team, not Project Zero. So what are we going to talk about? We're going to quickly go through first an overview of the Android OEM's ecosystem and sort of what that space looks like. Then we're going to talk about my lessons learned from beginning to reverse engineer pre-installed Android apps when you're coming from a background of reverse engineering user space applications. Then we get into some of the fun stuff of what type of security issues can you find and have we found in the Android OEM build images. So we'll talk about 4 different case studies there. So what's my goal for this talk? Overall, last year, our team reviewed build images from more than 1,000 different OEMs. And that is a lot of different build images in the Android ecosystem to be able to vet, to be able to hope to secure. So my hope is that through this talk, I sort of lower the bar of entry to reverse engineering and analyzing pre-installed Android apps so that we can have more and more security researchers making sure these spaces are safe for all of our users. And hopefully a part of that is I make it interesting, show you the complex and fun problems that we look at, and just sort of show that while we often talk about Android as a sort of monolithic thing, it ranges greatly from the diversity of all of those different OEMs and their capabilities and what sort of mindset they're bringing when they're building devices. So why do we care? Why do we need more people reverse engineering Android pre-installed apps? So by and large, each device comes with about 100 to 400 different apps pre-installed. So that is a lot of surface area that we need to be ensuring are secure out of the box. And it's harder to remediate these issues once they've launched to users because a build, the firmware image, things that are pre-installed are on a read-only file system. So in order to remove anything that might have security issues, it generally requires a security update to the device versus in a user space app, the user or an antivirus solution can delete it. Lastly, malicious actors are moving to infiltrate the supply chain. Because if you think about it from logic and return on investment, there's a lot of reasons why it makes sense for them to. Instead of trying to convince thousands of users to install your bad or malicious app, you only need to convince one OEM, one company to pre-install your application, and then you've infected at least a couple thousand users. And over the last couple of years, exploiting Android has gotten harder. So if those malicious actors want those privileges that they would have previously gained in years past through rooting or exploiting, that is much more difficult. So if they can trick and infiltrate the supply chain, that's a way for them to get those privileges. And lastly, as myself and my team were moving into this space, there's quite a few resources out there of reversing and analyzing user space apps, but we really didn't find the resources for pre-installed. So I hope we can all start adding that to what's out there. I do use some acronyms, so want to try and set the stage to bring everyone up to the same level. AOSP is the Android open source project. So that is the code that is completely open source for the Android operating system. So when I say that, oh, this is in AOSP, that's that baseline open source project. When a device is built, then Google, Samsung, all the different OEMs then generally add customizations on top of that. OEM is the company that is delivering the device. So again, like Samsung, Huawei, BB Mobile, all the different OEMs. ODMs are the people who build white label devices. If, for example, the long tail OEMs who are selling inexpensive devices, they'll often just put their branding on top of a white label device. Google Play Protect is the built-in antivirus solution. So my team has the ability that when we find bad apps, we flag those through Google Play Protect, and that propagates to all Android certified devices if the user has it enabled. And from the Google Play Protect perspective, PHA is sort of what we call malware, potentially harmful apps. So let's get into it. So what does the Android OEM, the pre-installed space, look like? We can really separate it out into two different categories. You have the certified devices. Those are devices where the OEM works with Google and licenses all of the Google apps. So the device comes with Google Play, Gmail, GMS Core, things like that. In order to get that certification, they have to go through an approval process, which includes a bunch of test suites. However, there's the other category of devices that, since AOSP is an open source operating system, those device manufacturers, developers, builders, they don't need or want the Google apps, and thus are just using the open source operating system for what it is. So an example of that is like the Amazon Fire tablet, where you won't see Google apps on it, and they have put all of their customizations into a new operating system. So those devices are just Android compatible. So this is all the different test suites that are currently included in the test approval process for Android certified devices. So the Android sort of tablets, or not tablets, like the Amazon Fire tablets, are devices that just want to be built on top of an AOSP. They only really need to go through the CTS test, compatibility test suite. And things like that are updated yearly with each Android release. And the main security tests that are within CTS is SE Linux policy tests. But if a device wants to be an Android certified device, so those are most of the big name brand Android devices you hear of, like Samsung, Google Pixel, all those devices, they have to go through the whole set of test suites. And the main one we're going to focus on is Build Test Suite, because that's where the security review and my team and myself came into play of trying to find PHA or security issues within these builds prior to them launching. So the goal of Build BTS and why it launched is to find security issues before they launch to users. And the main goal was to find anything known as PHA. And our definitions are listed at this website, but they are those user-harming behaviors, such as mobile billing fraud, spyware, Trojans, backdoors, things like that. And that continued to expand to a couple different things and has a roadmap, but that's been the main focus, and where a lot of these findings that I'm talking about in the case studies came from, and why we were trying to build up our reversing and analytical capabilities in pre-installed apps. While the goal is always to find things before they launch to the users, BTS happens right before it launches to the user. So it's the last step, because the firmware image we receive has to be the same one that goes out of the box. And therefore, the reality is when you're operating at a scale of seeing that many different firmware images, sometimes you find things after they're already in the wild, especially when you consider how many years of Android there's been. And so some things were already existing. And in those cases, we will immediately implement detections in BTS so that no new builds will go out, and then work with the OEM to issue security patches, as well as use Google Play Protect to immediately begin warning users. But let's get into some of the fun stuff in the reverse engineering. So this section has really come from when my team tried to transfer our tooling, our process, our knowledge base, some of our assumptions about how things would work and how it would transfer to pre-installed were wrong. So the goal here is to highlight some of the categories of wrong assumptions we had that hopefully will give you the most return on investment to start your pre-installed analysis. So the first one is dynamic analysis. As researchers, AVs, different things like that, dynamic analysis plays a big role in our ability to find bad behaviors. But when you're reviewing pre-installed apps, if you assume that the output of dynamic analysis is going to alert you if something bad is going on, it's often not the case. And there's a lot of different reasons why dynamic analysis doesn't quite work as you'd expect in pre-installed applications. So the first example of this is that there is, in the permission model for Android, there are something called signature permissions and privilege permissions. So a signature permission is only able to be used by an app that is signed with the same key as the operating system. So if you think about, the OEM is going to be the one that signs the operating system on that device with their private key, then only apps that are also signed with that private key, AKA should be the OEM's code, can then gain those signature permissions because they are pretty privileged and allow access to sensitive functionality in devices. The other type of sensitive permissions that we'll talk about is privileged. Those are maybe not the OEM's app, but a trusted party like a carrier or something like that. Their apps can be written to the system image on the device or system partition, which is the read-only partition in the priv apps directory. Then those apps are able to access privileged permissions. So example of some of the signature and privileged permissions are here. So pretty sensitive stuff, things that would not make sense for any user apps to be able to have access to. So when you consider how dynamic analysis pipelines often work, especially the automated ones to review apps at scale, is that they will sideload the application into the dynamic analysis environment and then try and run it. But in that case, if you try to sideload one of these preloaded apps into that type of environment, then it's not going to be able to access these permissions, and thus you're not going to see the behavior that is protected usually by those permissions. And because that's pretty sensitive stuff, you probably want to see what it is and understand why they need those permissions in the first place. The next type of issue that can cause your pre-installed app to not run correctly in dynamic analysis is that the app is running under a shared user ID. So they can declare this in the manifest, and it means that as long as all the apps declaring the same shared user ID are signed with the same key, then it basically looks to the process like a superset of all the code and all the permissions. So if you're trying to analyze that app as a one-off, then it's likely not going to run everything or at all. Another reason they don't run in dynamic analysis is that a lot of pre-installed apps are headless. So some of y'all might have been surprised when I said that Android devices often come with 100 to 400 pre-installed apps, because when you take it out of the box and you look at it, you don't see all those apps. And that's because they're headless, AKA don't have a user interface. But the problem is that the way a lot of automated dynamic analysis pipelines work is that they will automatically launch the launcher activity that is within the app. The launcher activity is designated in an app's manifest because it is the activity that is run when a user clicks on the icon, and that's what starts the app. But if the app doesn't have a UI, it doesn't have a launcher activity. And so in order to start or execute code for one of these headless apps, you usually have to do static analysis in order to find what activities and services or receivers have intent filters, and that's how it started. So any ways to be able to have it run in dynamic analysis, you're going to need to do static analysis to get it to that point. Not lastly, but this one's pretty obvious when you think about it, but when you have a pre-installed app, it can be competent, it's on a very specific device, and sometimes they're dependent on custom hardware. And while the hardware abstraction layer, or HAL, of Android tries to abstract a lot of this out, if your dynamic analysis environment doesn't have some of that hardware, or they're dependent on other customizations, it's just not gonna run. The final one, which is an interesting problem, is that if you're still dependent for dynamic analysis on sideloading versus, buying that exact device, then you, for example, can't really sideload a settings app or the dialer app or the system UI app into a new device and have it run effectively. So that's an interesting problem because yes, we have seen security issues and badness in some of those critical apps that have been modified. So how do you address this? And it's the favorite answer of, it depends, because it's going to depend so much on what your case is. For example, our team of trying to review tons of pre-installed apps from every different OEM, all the different devices, is very different from a researcher who's like, for 6 months, I'm going to do a deep dive into every pre-installed app on this one device. So that's where it is a different cases. So if you're that researcher that just wants to do a deep dive, then you can probably just instrument that one device, find that one phone, and then work. Whereas, for example, for us, we considered what might be the biggest bang for the buck in order to get the majority of apps running with smaller changes to the dynamic analysis environment. So for example, for the first one, that might be signing the dynamic analysis environment with our key and then re-signing each app we want to run. Another issue is app collusion. So we talked about this a little bit with shared user ID, but the main difference is that while this may happen sometimes in user space apps, it happens quite a bit in pre-installed apps because they know their environment. They can be confident this other app will exist on the device, or these binaries, or this OS modifications. So if you're going to try and analyze that app as a self-sufficient entity, it may have spread its bad behaviors across a couple different components. And instead, while we might still choose to analyze one at a time, we need to keep our minds open to look for signals that tell us, I need to look out I need to understand the rest of the components in the environment this app runs in. So an example of this, and this is what it looks like in practice for the shared user ID of two apps, is we believe one or both of these apps are doing what we call SMS fraud, meaning that it sends a premium SMS text message without the user's consent, thus charging their mobile bill. Not good. But what we see is app number one, when we begin to analyze it, it declares that send SMS permission, but it doesn't have any code or API calls to actually send a text message. App number two, on the other hand, doesn't have the send SMS permission, but it does have API calls to send text message, which those API calls require. And then you take a look at their manifest and realize that both of them declare the same shared user ID and are signed with the same key. So to the device, it looks like they're running as a single process with code that calls send text message, and they have the permission send SMS. And so together is how they're malicious, and each individually, though, appear to be benign. Another example of multi-app collusion is the use of custom permissions. So there's been some research calling out all custom permissions as bad, but I disagree because I think they are a way to really allow device manufacturers' apps to smaller segment protections to information or functionality. However, when you do see them, you need to be aware of whether or not they may be proxying permissions. So what I mean by that is we have this app. And in the app manifest, it defines a new permission, a custom permission. And it says that that custom permission is going to be dangerous. By the way you know it's defining a new permission versus using one is that tag at the beginning says permission rather than uses -permission. So this is defining one. It says the protection level is dangerous, which means any other app on the device may request it. It's not protected by the cert or anything like that. Then we see that the service that this app has is protected by that permission, meaning that any application that wants to interact with that service will need to request this permission. And that's fine, that's good. The problem comes in is if my service right here is doing a behavior that is protected by an even more sensitive permission, then we get into this proxying situation. So what this could look like, for example, is let's say my service was silently downloading and installing apps. That behavior is a signature or privilege permission, and it's called install packages. And it goes through a specific waiver process to be granted that. And now instead, though, they're letting other people access that behavior, and they only have to request this permission. So their other apps or components on the device could now get access to that very sensitive behavior, usually protected by a signature or privilege permission, by just getting this user space permission. Apps, though, don't only collude with other apps. Sometimes they will also expect and depend on behavior that comes from binary daemons on the device or even operating system modifications. So we'll talk about this in case study number 1, but apps can start daemons that are living in system/bin, or sometimes they just know they're running on a timer in the background and will interact with them at that point. And when on the second bullet, when we're talking about the operating system or framework, framework is the Android APIs. So part of the operating system in that respect of here are the Android APIs in this example here. Triada, which I won't talk about in depth today, but there's a lot of information out there and about it, is what they did for that backdoor is they modified the Android log API to be overloaded and allowed 2 arguments. So if any app wanted to interact with the backdoor, they sent a second argument in log, and that's the type of modification we're talking about. Another thing that we ran into when beginning to reverse engineer pre-installed apps rather than user space apps is that pre-installed apps are supposed to operate in a more privileged context. And so we had for years and years and years fine-tuned our detections, our process, our scores, ML models to identify badness or PHA in user space apps. So something like this might be, let's say we have our SMS fraud ML model, and it's looking for things that are sending SMS messages. When we began trying to apply all of these scores and detections to pre-installed apps, we had a huge amount of false positives. So many sometimes that it was really hard to wade through because a lot of these scores and detections were on the lookout for anything that looked too privileged or looking out for apps that pretended to be system applications, as a lot of Trojans do. So my suggestion to you is if you want to begin applying your tools and things like that to pre-installed apps, do it in small chunks at a time so you're not overloaded with false positives, and probably begin to think about what does SMS fraud look like in a pre-installed context so that you're not, for example, flagging the messages apps on devices. So I know this is what a lot of people are interested in. Let's talk about what this really looks like in practice and sort of the variety and range of how different security issues can manifest on the wide variety of devices that make up the Android ecosystem. So the first case study we're going to talk about is 2 different examples of arbitrary remote code execution backdoors. So when I say arbitrary remote code execution, first what I mean by remote is a little different than in some contexts, is we consider remote if it can be commanded or controlled by any other application on the device. And while that might not go with some of the other paradigms, the reason why is because it's to be more cautious in user protection, because it's not that hard to get someone to install a user space application. And if a user space application is on a device and able to command and control or any component, that's concerning. Arbitrary means that it will literally run any command that the commanding entity wants to. And just for information, some of the common APIs to look out for when looking for command execution is if you're in the Java Kotlin realm within apps, it's runtime.exec and process builder are the most common APIs. While if you're in native code, you have all of the Linux ones, but some of the most common we see for pre-installed is system. So example number 1, what was it? Complex diagnostic software that was left on production builds. Joy. So it had 4 different components, and that's why I say it's complex. It had a pre-installed application, 2 different types of native daemons running on the device, a modified SE Linux policy to allow the command execution to be more privileged than is usually possible, as well as a custom kernel character device to enable it. So this is what the flowchart looked like. We had our pre-installed application. The app is the one that communicated with whatever remote entity through a socket. It would also send information off the device based on some of the commands it executed and what was returned via a hard-coded email address. So this is the code from the pre-installed application. At the top, we see it connecting to a socket. Then it's basically sort of a handshake thing. The remote client needs to know, I believe it's 7 times to hit enter as the app sends different device information. And then at the bottom, Finally, after hitting enter 7 times, the remote entity can send a string. It's base 64 decoded and then sent to this procdm string method. Procdm string then just directly writes that string with no sort of processing into a text file that lives in the app's cache directory. Then we have our first daemon, and this is where the modified SE Linux policy came into play. Then this daemon goes into the apps directory and reads that text file. So what we see is at the top is the actual code in the native daemon, and at the bottom is the bash command that it actually generated. So what they're saying is, once this text file exists, then cat its contents directly into this kernel character device, then remove the file. So that's what I meant when I said there can be collusion, of that the app knew that this daemon would be running in the background to gather the contents that were received from the socket. Then we have daemon number 2. Daemon number 2's job is to process the commands received from the socket. So it's constantly monitoring the kernel character device to see when new information is written there. And whenever information has been written there, it processes the information. What's most interesting to us was that if the string received from the socket was encapsulated by 2 tags, EXXSH and the closing EXXSH, it immediately passed what was ever in between to system. So that's really not good. This is what it looked like in IDA. At the top, we see it looking for substring between those 2 tags, and then it just passes directly to the system syscall. So what do you do when you find something like this? We found this the very first day that OEM began submitting to BTS, but because BTS was a newer thing, it had already gone out in some devices in the wild. So it did end up affecting 223 different build fingerprints. The build fingerprint is basically the ID for an exact firmware image across 16 different SKUs with about 6 million affected users. But what sort of did give us hope is that 70% of those affected users did have an OTA update available within 2 weeks, and 100% had one available within 1 month. And if a user had Google Play Protect enabled on their device, while GPP can't remove the app due to it existing on a read-only file system, it was able to disable the application. Now we have another example of arbitrary remote code execution. And this one looked very, very different than the first one because it was self-contained wholly within a single pre-installed application. And the purpose of it was to be a diagnostic software used for remotely managing a large fleet of devices. So this was not actually the normal user Android handheld, like a mobile phone for users. It was used in sort of enterprise factory industrial control system environments. And that's why as soon as we reported it to the OEM, they filed for a CVE, as well as then there was an ICS advisory from US CERT that went out. So how did this manifest? And it was actually, I didn't mean to do that, but it was actually the bug was in the manifest. So the first thing we see here is that it is running a shared user ID system. Shared user ID system is the most privileged process on an Android device besides root. So if you see something running as system, nominally it has access to every single permission on the device, since remember, shared user IDs mean it is the superset of all the permissions of all the code that are all superset of the permissions. The next issue came is that they have a service, and in the manifest, they set this service to being exported equals true. And what that means is when a service is exported, any other component on the device is able to start it, bind to it, stop it, etc. Any sort of those interactions. So if we take a look at what that service looks like, the key is that they have set a binder. In Android, binder is one of the IPC mechanisms, inter-process communications, and it's kind of like a server-client paradigm type of thing. So this means that any component on the device can call on bind and receive back this binder object. The binder was this system operation service $3 class, which it defines a whole bunch of methods that now the client process, which has requested that binder object, they can directly call. And it had a lot of methods that were defined to be able to be directly called. But of course, exe command was very concerning because it's running as this privileged process system, and now a client, aka any other component on the device, is able to call exe command, whatever command I want it to run, and it is directly passed to runtime.exec. But this proposed sort of an interesting detection problem to me that I just thought was interesting and fun. The fix for the OEM to this is to add a permission protecting the service so that only other of their code is able to call this. And that means this fix, in the fixed version and in the backdoored version, all of the executable code is exactly the same, which we were always trying to create detections to detect the bad behaviors, the actual bad execution, what's the harm that's being done, rather than static signals. So this kind of just threw all of us for a loop of you can have a app with security issues and an app that is benign, and they have the exact same executable code. So just an interesting sidebar. So that's two examples of remote code execution. Then we get into a different type of issue. In this issue, the OEM modified the framework, the OS that includes the Android APIs, in order to do URL logging. So this was actually discovered by Łukasz Siewierski, aka Maldroid on Twitter, and he's around here somewhere. And what they did is they modified OS and application in order to get access to every URL that was visited through WebView. And thus, that's spyware. So what this looked like in practice is they modified the framework classes in order for each of those to send an intent every single time those framework APIs were called with custom data. And then they had their own logging app that registered a receiver for that intent so that they would receive it and be able to read all that sensitive data that they wanted to log. And then they uploaded it sometimes. So the other problem, if this wasn't enough, is that they were sending these intents in an unprotected way, which meant that while they only intended for their logging apps to be able to grab this sensitive data, in reality, any application on the device included user sideloaded apps, malware, anything like that could grab this if they knew what to look for. So what do those framework modifications look like? One example is that they modified WebView, as I said. So every single time WebView went to load a URL, they then sent an intent that contained two extras. One was the URL they were intending to load, and the other was the application's package name that was intending to load it. They also did this for the activity subclass, which is run just about all the time. So again, they were trying to track when applications were switching, who was in the foreground, who was in the background. And so the issues and why they had to go down to the framework level was that a single logging app based on the Android sandbox should not have that type of app-sensitive data. So here's a sidebar. If you've been reverse engineering Android, working in user space apps, then you often haven't gotten into framework code. And so framework code can be a little bit intimidating to begin reverse engineering. So hopefully this can help share. So first, framework code is generally living in the system/framework directory on the device. And it is probably one of the directories that changes the most with each new release of Android. So between, in what letter comes after N? O, P, Q, things like that. And the file formats change a lot too. So these are all the different types of file formats you might find. Thankfully, there are a lot of open source tools out there for recreating ODEX, VDEX, things like that back into DEX files, DEX bytecode files that then you can begin to reverse engineer. So one of my big suggestions for framework while for everything else that generally is run as DEX bytecode on the device, like apps, we're able to decompile back up to Java. I have found that it's often much easier to reverse engineer and analyze framework code within Smalley. So if you're new to reversing Android, Smalley is sort of the equivalent to assembly in the DEX bytecode world. So if you have DEX bytecode and machine code, then Smalley is the human readable version of DEX bytecode without being decompiled Java. People don't like it also when I usually say this, but the best way I have always found to figure out which of the hundreds of framework files to begin reverse engineering is grep and string search. People usually want a more fancy answer, but in reality, that's what I found. And if you're looking to find ways to contribute to the community, a tool that I think would be really, really valuable for all of us to audit these many different devices and frameworks is if we built a full tool to be able to diff framework files on a device with the vanilla or clean AOSP, just to know what type of customizations have been built on top of this. Have they added advertising SDKs into the operating system or made these types of changes that enable really scary, spyware-ish stuff? Yeah. So the next case study we have is security settings misconfiguration. So what happened is there were a lot of devices disabling Google Play Protect, which Google Play Protect has also considered that behavior whenever it happens without user consent as privilege escalation for many years. And so in order to disable or enable Google Play Protect, this happens through two settings that were hidden but still accessible to OEM code. And so for many years, there have also been put into place what we thought were a lot of detections to find this behavior. And it was for looking for apps that were modifying GPP through this type of command line command. Settings put package verifier enable 0. But that's how user space applications try to change that setting. Privileged apps are able to access the privileged settings APIs, and thus they don't have to do it through the command line method. They're able to request the right secure settings permission and then use the official APIs in order to change that setting. And that makes sense to have access because users need the ability to flip a switch and turn things off or on. So of course the pre-installed apps would access it. But what we didn't realize was that just about everyone was doing this and disabling it silently. And why were they doing this? And it was because back many, many years ago, I believe it was either 2013 or 2014, when at the time it was called Verify Apps, beginning to launch, there was a consent pop-up if you did not go through the full setup wizard process in order to ask you on your first apps install, do you want to enable the package verifier? And this prevented people from automatically provisioning a fleet of devices because you needed a human to go through and click through each of them. So some OEMs, as well as within AOSP and GMS Core, Google had done it as well. It would temporarily disable it and then attempt to disable it, and then attempt to re-enable it after they got through the setup wizard process. But what this led to is what made sense back in the early days, many years ago, became a at-scale privilege escalation issue. Because while most were trying to re-enable the setting, it wasn't all the time, and there also turned out to be a race condition that sometimes it couldn't be re-enabled. So this was a huge undertaking in operation to get fixed. And so the first thing was, this was done in AOSP. And so this CVE addressed it to get it fixed, and that went out in the Android Security Bulletin in January 2019. We also fixed the code in GMS Core to fix this, and then did a lot of communications with every single OEM to make sure that behavior was removed from new builds. And I think it's just important to remember for all of us as security researchers of we're often adopting legacy code. And it's funny to say legacy when Android's only 10 years old, but things change fast in our industry and what we know about security. So I think it's important that we all remember with our new tools, with our new knowledge, to go back in time and look at what might have changed in the years since. So the last case study is very different than the other three because this is pure malware. Third-party botnet, aka Chamois, that was included in quite a few different devices. At its peak, Chamois had hit 20 million infected devices, and that was through both pre-installed and user space applications. So what's Chamois? Chamois is a botnet whose payloads include premium SMS fraud, click fraud, other types of ad fraud, app installation fraud, and arbitrary module loading, and that so that they can, evolve and develop new capabilities of their payloads, and thus GPP flags it as a backdoor. Earlier this year, I did a detailed talk on Chamois because we did consider it the most impactful botnet of all of 2018. And largely one of the reasons why it was so impactful is the way it infiltrated the supply chain and thus became pre-installed. So this is Chamois, super simple botnet, right? This beautiful chart was created by Remy Adeber, Halfer on Twitter. And so it's a super complex capability. But what we're going to focus on in this talk is its supply chain distribution methods. So OEMs and ODMs were tricked into including Chamois apps, or in some cases, just a SDK of stage one. So is that going to... Okay, I can't go back. But just an SDK of stage one. And they were generally told it's a mobile payment solution. It's an advertising SDK. And I think this is one of the important factors of remembering the diversity of OEMs that are in the Android space. So there are some long tail OEMs that sell, $30 devices, $40 devices, and have almost a negative margin. So a free solution or an advertising SDK is how they do make up some of their money. But then the threat actors know that too and try to prey on that need. And so, so they generally had pre-installed two different methods of distribution. One was the stage one Chamois APK was statically pre-installed on the device. It was also often named like sales tracker or something like that. Otherwise, they pre-installed an application that would then dynamically download and execute the Chamois SDK. So there were sort of two distribution methods in the pre-installed supply chain ecosystem there. So Eager Fonts. Eager Fonts is a fonts application that was included by a SOC vendor in their platform from a third-party developer. So the reason why they chose to include it was this fonts application was wanted by a lot of people. It allowed all the OEMs who used that SOC platform to have much better internationalization with a lot of different fonts for all the different languages they were trying to support. And so turns out this fonts application then included an advertising SDK, and that advertising SDK didn't actually show ads. It did DCL, aka dynamic code loading, to download from a third-party server plugins that then executed in the app context. And the plugins from Eager Fonts were of known malicious Trojans. The most common one was Chamois, and the next was Snowfox, which is a Trojan in click fraud, and others. But because these actors had gone so far up the supply chain to infiltrate a SOC, not even a single OEM, it ended up affecting all of the different OEMs who used the preloads from that SOC, aka 250 different OEMs across 1,000 different SKUs of devices. So thankfully, as soon as we identified it, contacted them, the SOC platform immediately also began contacting all of their customers. They pulled the app and they agreed to no longer include any third-party preloads into their platform due to the risks. So trying to learn and grow from each of the different issues. So this is what it looked like. Eager Fonts sent an HTTP request trying to say it's an upgrade the app, and they received this type of response. The response included the URLs, names, and the actions to complete for each of the different types of plugins that they were supposed to download. And then the SDK used Dex class loader to dynamically load the downloaded plugin within that pre-installed apps process. So what type of remediation do you do when 250 different OEMs are affected? So we did have a OEM remediation process, which first is alert the OEM, require an ACK, acknowledge that, yes, this was on my device. 2, immediately require OTAs to be developed and distributed to users. And next, which I think has been one of the most powerful, is require a postmortem to determine how did this issue even end up on your device. And I think that's valuable because that's how we know how these OEMs were being tricked, what they were being advertised as what they were including, and just better understanding the threat landscape. And then they also then have to create a plan for how do you actually prevent this from happening in the future. So for a lot of them, it's, for example, don't include third-party preloads, different types of additional auditing, things like that. So by the numbers, these numbers differ slightly from what I presented at Kaspersky, because Kaspersky was all devices infected, where this is the pre-installed affected devices. So in March 2018, it was 20 million devices as a whole were infected with an active version of Chamois, and of those 27.4 were pre-installed. As of July, at least, it is now continuing to decline it's continuing to decline and below 700K, and we will keep working and tracking it until it is hopefully zero. But part of the problem and things we learned is that around the world, taking updates in OTAs is not as common as it necessarily is in the US or Western Europe. So and that's what sort of lights the fire of how can you find all these issues before they ever go out? And also really understanding the diversity of the space. So in conclusion, first, I hope I've piqued your interest a little bit in trying to help reverse, secure, analyze the Android pre-installed space in these apps. It's a lot of fun. There's a lot of different problems and complexities to find and solve. And I hope that I've also lowered the bar in understanding that there's a few key things to think about and to challenge your own assumptions of what does security badness look like pre-installed versus user space. So hopefully you can get involved more efficiently and not make the same mistakes I made. And lastly, the Android ecosystem is pretty vast with a diversity of different OEMs and sort of capabilities. So you have some OEMs who have secure development life cycles beginning just at design with lots of security engineers on process. And then you have some OEMs on the long tail that might not have a single security engineer. And so the threats for each of those are very different. And what are you looking for and how are you using your time effectively to try and reverse and secure these devices? And with that, thank you. And are there any questions?